and also show you some recent results, very recent results, in which we also find some details and some structure in the Hubbard bands, etc., in spectral densities in the models for correlated systems, and we hope that this can contribute to further analysis and to understanding these systems. So please let me know if you don't see the slides, but let's see where I can't change. Yeah, okay. So this is where I am now in Bariloche in Argentina, in the south of Argentina. So I can see snow outside, it's winter time, and this is the ski resort with beautiful mountains and landscape. And here's where we are in the south of Argentina in Patagonia. So the motivation, of course, I mean, in this community, I don't have to say it, but just as a warming up, we all know that materials with strongly correlated electrons have these fascinating properties like high DC superconductivity, metal insulator transition, magnetic and electronic properties, the heavy Fermi behavior, and sensitivity, high sensitivity to external fields, etc. So, and they have potential applications. There is a great interest in interacting models that have several bands. Lately, there have been many publications and a lot of research interest in these systems. In particular, where we have a combination of localized and itinerant electrons. So, as we know, iron-based superconductors, transition metal oxides like ruthenides, manganites, vanadium compounds, helium bilayers, 4F and 5F rare earth heavy Fermi materials like cerium-based compounds, ytterbium, and also uranium, plutonium compounds. And I mean, just to mention a few. All these systems can give rise to multiplets, in-gap states in the electronic densities of states or electronic structure, as we can see in several experiments, and also to interest in orbital selective Mott transitions, in which one of the bands becomes a Mott insulator and the other bands remain conductive and metallic. These systems are very difficult to tackle theoretically, and due to, of course, the many body physics. I think theory is lagging behind experiments, and we still have many things to do, a long way to go in theory, because it's very difficult to tackle, but I think we're on our way. So this is our, to begin with, this is where we start, our standard model in condensed matter, which is the theory of everything, let's say, of our topic and our area. And where we have itinerant electrons, probably you can see my pointer here, itinerant electrons in an array of ionic potentials and interacting via the low-range Coulomb interaction. So this is very difficult to handle, mainly due to correlations between all the electrons. So, well, the DFT, the density functional theory, and the Kohn-Sham in the Kohn-Sham theory is a very good ab initio method, which is where the approximations made is good for weakly interacting systems or intermediate, but it turns out not to be so good and not to explain these systems for larger correlations. Sometimes we have to resort to approximations, and so we can also model these systems with effective interacting parameters, and we can define models like the well-known Hubbard model, a single orbital Hubbard model, or with several orbitals like the Kanamori Hubbard model, which, for example, here I just give one because there are many, of course, many models for different materials, but the Kanamori Hubbard is very widely used for systems like the ones I mentioned in the introduction that have, for example, these T2G orbitals. And here I give an example of this Kanamori Hubbard Hamiltonian we have to solve, which has a kinetic term and an interacting term. The interacting term has a local impurity, a local interaction U for W occupation, and has also orbital Coulomb interaction, effective Coulomb interaction U prime. And it also has a Hund's J, which is ferromagnetic in most materials, that promotes parallel spins between different orbitals. This J has two terms in this model. For example, that has a spin flip term here between different orbitals. And it also has a pair hopping term between the orbitals. Here there's a sketch. Of course, it's not one-dimensional. It can be 2, 3-dimensional. Here we have 3 orbitals. We have the electrons in red and holes in blue. And when we have a W occupation, we have a U. We also have a U prime between different orbitals, and a U prime minus J that promotes, as I said, ferromagnetic interactions. These orbitals can have different hopping integrals, T1, T2, T3, and they can be degenerate or not. They can be equal or not. If one of them is too small, one hopping is too small, then one of these bands can be insulating, while the others are metallic, giving rise to the orbital selective mode transition I just mentioned. So this is a very complicated Hamiltonian to study, and not only Hamiltonian. If we want to try to treat more realistically materials, it's a really formidable task. Our goal is to try to understand the complex microscopic behavior in these systems, which leads to these fascinating properties we were talking about. So we need to count with powerful analytical and mainly numerical tools to deal with these systems in order to get results to compare with experiments. This is not new. I mean, this is our main goal. We're all working into this. But in my view, now we're currently witnessing very important improvements in numerical methods for these correlated systems to delve into the microscopic details. In this talk, my objective is to review briefly some of the latest developments in these numerical methods. To calculate, I would concentrate on densities of states and electronic spectral densities. By looking in the literature, of course, there are many different ways of calculating electronic spectral densities, but we are not able to delve into the details, and we're just only now trying to get access to results and observed structure in, for example, the Hubbard bands or in the different bands that constitute these materials. So this is very, very promising, and I would like to show you how this went evolving with time. Well, I'll concentrate on one of the methods. Of course, it's not the only one, but it's one of the most used and reliable methods to calculate electronic spectral densities in these materials, which is the Dynamical Mean Field Theory, the DMFT. I don't want to get too technical, but just because I know they're experimentalists, I mean, this has been around for several years, since the late 80s, early 90s, and this method consists in projecting the whole interacting system, either the model Hamiltonian or having input from the real system from DFT, from ab initio. So we can input, I mean, we can get a whole modeling of the system and project it onto an interacting impurity, which is here says atom. This impurity now is an effective impurity that is interacting with a non-interacting bath, which we call effective medium, and is interacting dynamically via, I mean, Green's functions we have to calculate, and with a self-consistency condition. So this is a DMFT, this mapping of the whole system onto an effective atom interacting with a medium. Of course, this is exact in infinite dimensions, as was shown in this paper long time ago. And the main approximation is the self-energy, which is local. So here, the self-energy that comes out due to interactions is local. It only depends on omega, the energy, and on k, the momentum. This is the main approximation of the method, but there have been important developments and extensions of this method to trying to understand it, to having a non-local or at least not so local self-energy by having a very complex impurities, effective impurities, by considering many sites, for example, 4 sites, 8 sites. So this is called the cellular or the cluster DMFT. And so then the impurity will be a complex, a very large system full of levels that we have that will be called this effective impurity or the atom. So within the DMFT, so the DMFT, as I said, is has consistent equations like this. So this is, I mean, I don't want to go into these details, but one has to solve it self-consistently, and at one point one has to solve this effective impurity. What does it mean to solve it? We have to get the dynamical response functions. We have to get the Green's function of this impurity, and this impurity, remember, the impurity concentrates all the interactions of the model or of the system. So the impurity solver is very important here, and it's at the heart of this DMFT method. And there have been several impurity solvers since the beginning of the DMFT, which are listed here. I mean, not all of them, but in the beginning we had the perturbation theory solvers. One can solve the impurity. Remember, we have a correlated impurity with a non-interacting bath. So this effective system now has to be solved. We can solve it with exact diagonalization. So this can we can get to include interactions, but get to relatively small systems. Hirsch-Phi quantum Monte Carlo systems, non-crossing approximation, numerical renormalization group, and more recently, methods based on the DMRG, which is the Density Matrix Renormalization Group, or in its matrix product state representation. I would talk a little bit more about this because we developed this several years ago, and also together with Eduardo Miranda about already 15 years ago. And another methods based on this MPS, which is a time-evolved block decimation, etc. So there's a very important method, which is a continuous time quantum Monte Carlo, which is very widely used nowadays. Also flex, confirmation interactions, and other methods. You see that solving this correlating impurity is so important that there have been many developments of impurity solvers for this method. Some of the problems is that, for example, the quantum Monte Carlo methods to solve the impurity. You know, this we have to calculate Green's functions. The Green's function is a complex function defined on a complex plane, which is the complex plane. We have omega and I omega, and the Matsubara frequencies are on I omega, and the quantum Monte Carlo methods converge on the I omega axis. So if we want to get results for densities of states which are defined on the real energy axis, the results that are converged in the DMFT on the I omega axis have to be analytically continued to the real axis, and this is ill-posed. It can give problems, and it's very difficult to control. However, quantum Monte Carlo methods are able to tackle final temperature that cannot be tackled with some of the other methods. The other methods that can give more information on the structure of density of states, which are defined directly on the real omega axis, that's our aim, are, for example, exact diagonalization or numerical renormalization group, or our DMRG solver, and this gives directly results on the real frequency axis, and they converge on the real omega axis. So that's why we think that these methods can lead to a more precise description of densities of states. However, they're not able to treat temperature, so they are complementary to methods like quantum Monte Carlo. So I think that these methods are complementary, and depending on what we want to see, one can use one method or the other. So let me give you some examples. For example, this is a resolution of the one-band Hubbard model several years ago using the numerical renormalization group. And this is a half-filled one-band Hubbard model. Here we have the typical three-peak structure for this model in the half-filled case. And here we have the metal to insulator transition we have the lower Hubbard band, the upper Hubbard band, and the coherent conduction peak at the Fermi energy omega equal to 0. This will always be the Fermi energy. We have particle-hole symmetry, and so cranking up U, we have the metal to insulator. This is a MOT insulator. We have a half-filled band. As you see, this numerical renormalization group, which counts on a logarithmic discretization of the energy bands, concentrates mainly on low energy properties, but it is able to get some feature in the lower and upper Hubbard band at the inner edges of these bands for the metallic state. When the metallic state disappears, we have no feature. Now recently there has been a very important improvement using exact diagonalization for this effective impurity. So remember, we're concentrating on solving this effective impurity, which has all the interactions and it's interacting with a non-interacting band. It's hybridized to a non-interacting band. So we have to solve the Green's function of this impurity. Here we have again the one orbital Hubbard model on a beta lattice, and this is cranking up U from U0 to 1.25, and here we have a narrowing of the peak, and this is using exact diagonalization by a group of Gunnarsson, where they can reach very large systems with several hundreds of sites by rotating the non-interacting path to an appropriate basis, like is shown here. I won't go into details, but this is a very nice improvement of the exact diagonalization. However, I mean, here is they're comparing their results to the results of NRG, which is seems quite reasonable, and they do also find some features. However, it might be difficult to treat much more complex impurities with this system. So this DMFT is not only able to tackle, to study model Hamiltonians, but also to treat more realistically systems like this compound, for example, the ruthenate, strontium ruthenate, in which in the DMFT equations, one can include the spectral density obtained from ab initio calculations, which, as I said, do not treat interactions very efficiently. But the DMFT can get this information of the spectral densities, and then one can start with the DMFT self-consistent equations and converge. So one includes, within the DMFT, one includes the interactions and add them to the ab initio input. So here we have some results by Eva Pavarini's group, in which they use the quantum Monte Carlo as impurity solver. As I said, this quantum Monte Carlo converges on the Matsubara frequency, and the problem with quantum Monte Carlo is that it cannot get to very low temperatures. So here this calculation is for a temperature of 290 Kelvin for this material. The Fermi liquid properties arise at temperatures lower than 25 Kelvin in these materials. So the temperature is really infinite compared to the Fermi liquid temperature. But however, one can have an idea of what's happening, but one cannot see Fermi liquid properties here. The results here are with LDA spectral densities as an input, including spin orbit coupling, with the DMFT. These are this black and gray line, and compared to the bare LDA plus spin orbit, which are this light blue line. So one can see how DMFT really improves the LDA results. However, now this temperature can be lowered in this calculation here by this group in this paper. This is a very recent paper from this year, in which they also treat the strontium ruthenides with the input of ab initio for these three, for the 3-band Kanamori Hubbard model. Here, in this result, there is no spin orbits coupling, but they can include it. But here they are using NRG as impurity solver, and so again, the NRG converges on the real axis. We can have much more detail of the density of states, and we can reach 0 temperature. So this is an improvement to the previous result I showed. The full lines, red and blue, are the DMFT results using NRG as impurity solver compared to the other lighter curves, which are the bare DFT results. So you see there is a big improvement of the data. These are typical results from NRG calculation, where one can see very spiky curves in the density of states close to the Fermi energy. And this is typical from the logarithmic discretization of NRG. As a last example, I want to show you this result by a group of Gabi Kotler and Howley 10 years ago, where they also use a DMFT, of course, and using the LDA as input for these chalcogenides and pnictides. And they want to study valence fluctuations and densities of states. They want to try to find structure in the densities of states, and they find it in the chalcogenides and not in the pnictides. Here you see they compare with experimental results. The experiment is in blue, and here you see some structure in the experiment. The Fermi energy is here in the middle at 0, and their calculations, the orange is the theory including projected onto the F band of plutonium, and the other broken line is all the rest of the bands, SPD, which are featureless, but they are able to see the features in the density of states using an extended, an improved non-crossing approximation, and comparing to slave bosons. So here they are able to see multiplets, which are remnants of the atomic structure in these materials, which is interesting, and they can compare with experiment. Now, I want to show you our results. So several years ago, we thought of an impurity solver based on the Density Matrix Renormalization Group developed by Steve White several years ago, which has become one of the main methods to study correlated systems, mainly in low dimensions. So this, I like the quantum information perspective to understand the Density Matrix Renormalization Group, the DMRG, which uses, appeals to quantum information to keep the most relevant states. So one way of interpreting the density, the DMRG, is that while we increase the system size, remember we want to solve the effective impurity with a non-interacting bath. So we have a finite number of bath sites, and we want to increase the number of bath sites to be able to solve this impurity effectively. Of course, the Hilbert space grows exponentially, and this is the DMRG developed by Steve White, uses quantum information to project and to keep the most important, the states with heaviest weight, or that carry most information in our quantum system. So as we enlarge the system size, we only keep the states with more information. The importance of quantum information concepts for many body systems was emphasized by John Preskill 20 years ago, saying that the most challenging and interesting problems in quantum dynamics involve the understanding of the behavior of strongly coupled many body systems. So better ways of characterizing the features of many particle entanglement may lead to new and more effective methods for understanding the dynamical behavior of complex quantum systems. This concept synthesized by John Preskill, I think, is very important, and this is right behind, at the heart of the DMRG, and later on in matrix product states and tensor networks that are currently very widely used. So this is what we did. We can calculate complex impurities in these 3 different settings, or even more. I mean, but these are just examples. For example, the square is the impurity, the interacting impurity coupled to a non-interacting band, which are the circles. Here we have 2 impurities, so the whole thing will be a complex impurity coupled to non-interacting band. Or here we have an impurity with 4 levels coupled to non-interacting band, each impurity with its band, or even crossly connected. For example, this impurity with 2 bands can be a cluster DMFT. For example, if each impurity is 1 single orbital, this can be 2 sites in the 1 band Hubbard model. or it can be a two-orbital, a single site with two orbitals, for example, for a two-orbital Kanamori-Hubbard model, or if we take three of these squares, it can be the single site, three-orbital Kanamori-Hubbard model, etc. These are the effective Hamiltonians, and I won't go into details here. What are the advantages of using this DMRG or MPS impurity solvers? The advantages compared to our previous methods are, for example, as I said already, they converge on the real axis directly. So if we want to get response functions on the real axis, we do not have to resort to ill-posed analytic continuations, maximum entropy, etc., like in the quantum Monte Carlo methods. So this is very important to be able to converge on the real axis. One can treat all frequency scales, not only low energies close to the Fermi energy, but also at higher energy scales, and we can expect to get details for higher energies. Differently, as the NRG, the numerical organization group, mainly concentrates on features close to the Fermi energy, although now they are very efficient NRG methods, which can also include some information of higher energies. I'll show you some. We can also calculate arbitrary interactions, not only low interactions in the impurity like other perturbation methods. We have no fermionic sign problem like quantum Monte Carlo technique, especially when one considers several bands and one has hybridization between the bands. One can bump into sign problems that come because of the quantum Monte Carlo method. So this is a drawback of the quantum Monte Carlo. We can get large non-interacting baths for this quantum impurity model. For example, exact diagonalization cannot get to large baths except for the example I showed you by Gunnarsson and co-workers. But this is for a very special situation. We can look at several orbitals. We can look at several sites, so looking at cluster or cell DMFTs, and this gives us the K dependence of the densities of states, so we can get spectral densities. And the problem is that we still cannot get final temperature. So in this sense, again, it is complementary to quantum Monte Carlo methods. This method has been developed in these publications. After that, there have been several other developments of impurity solvers based on MPS, matrix product space, or tensor networks. I'll show you some examples, and these are important developments by Uli Scholberg, Parcollet, McCulloch, and Wolf, for example, where they use Chebyshev expansions of the Green's functions. And it also converges on a real frequency. And again, they show results on the two-band, for example, Kanamori-Hubbard model, half-filled. So this is the Fermi energy. And here they show their results in violet compared to the NRG or quantum Monte Carlo. So it's quite good. It doesn't differ much. And for the quarter fill, for example, here they have the doped system, again, the two-band Kanamori-Hubbard model, and they get this. But as you see, I mean, the spectral the densities of states are quite broad. They have some features, but then I'm stressing this because we were able to find much more detail in this with a detailed DMRG. This is another MPS kind of development developed by Paschate and co-workers. This is called a time-evolved block decimation, which is also based on MPS, matrix product states. And they calculate for the one-band Hubbard model, the two-band Kanamori-Hubbard model with these parameters for the half-filled system. So here we see again the three-lobed thing, lower Hubbard band, upper Hubbard band. And in this figure on the right, they compare with quantum Monte Carlo results. Their result is a violet one. And they can see again this feature in the inner edges of the Hubbard bands, which cannot be seen in quantum Monte Carlo results. These inner edges have also been seen in previous calculations. So this is the spectrum. This is the detail in the densities of states which can be seen with these methods. An interesting development was done also some years ago, which is the impurity solver on the imaginary axis, on the Matsubara imaginary time, but it's equivalent to converging on the imaginary axis in the DMFT, using also MPS, matrix product state. So what they do here is they converge on the imaginary axis, and then once they converge, then they run 2 or 3 times on the real axis. So they use the converged parameters on the imaginary axis to run on the real axis. Here's the applications for the 3-band Kanamori-Hubbard model, and this is quite impressive because they have 3 bands. So what is called one site means the 3 bands in a single site, which shows a metallic behavior. But if they get 2 sites, so it's 3 orbitals and 3 orbitals as effective impurity, then they get an insulator, and they get some structure in the Hubbard bands, in the low and upper Hubbard bands, by keeping very few states in the bath. And that is because when one converges on the imaginary axis, there is much less entanglement or even no entanglement, and it's much easier to do the calculations with MPS. However, the calculation on the real axis still has to be improved. They compare their results on the imaginary axis with the real and imaginary part of the self-energies as a function of Matsubara frequency. This is the imaginary axis, with quantum Monte Carlo results, and here they're indistinguishable. So as you see, the real and imaginary part are very smoothly behaved on the Matsubara frequency. But so then here you can see that getting structure and more detailed information of the densities of states on the real axis from the extrapolation of the conversions on the imaginary axis is very difficult, because the behavior on the imaginary axis is always very smooth, and it's much easier to converge to. Then there's also an important development I want to mention, which is called the fork tensor product, which is based on tensor networks to solve the impurity, done by this group. And they also solve the multi-orbital, the 3-orbital Kanamori-Hubbard model with DFT input for strontium vanadium, and they get the density of states for the doped systems in red compared to the light blue continuous time quantum Monte Carlo results that are brought in from the imaginary axis. So the agreement is quite good, but with the tensor network method, they have some structure in this in the upper Hubbard band. So that looks promising. Here they compare their results using the same tensor networks. This is a Fermi energy, and they compare to experiments. The red curve is their results. So what we have below the Fermi energy is photo-emission spectra, the blue one from experiment, and their result in red, which is quite good. Here we see some structure, and above the Fermi energy, they compare with XAS, so X-ray absorption spectra, with experiments in green, and the experiments they can distinguish the origin of these different, so very broad peaks. They come from EG and T2G bands, and something can be seen from the DMFT tensor network result. So this seems to be quite promising. This is done for the 5-orbital Kanamori-Hubbard model with these parameters, with input from ab initio spectral densities. So let me just go back to our results. Then towards the end of the talk, I just would like to show you our results and how we were able to get real detail on the spectral densities with the DMRG solver, impurity solver. We studied the 2-orbital Kanamori-Hubbard. So it's like the one I showed in the beginning. We have 2 orbitals, and our impurity effective impurity has 2 orbitals. We have a local U. We have hop-ins. We have 2 different bands. One band is wider than the other, or they can be equal. The chemical potential And we also have the interaction, which has the local Hubbard U. We have an inter-orbital U2 or U prime, I was calling it U prime, the Hund J, and also the spin flip and spin double hopping, double particle hopping. So to simplify the model, we have we consider J equal to 0. So first we get rid of the J interaction, and we only keep the local U and the interorbital U prime, the interorbital Coulomb interaction U prime. We consider two bands. One band which would be very wide, and the other band which will be narrower, and we want to look at the orbital selective mod case. The results we get are the following. Of course, if the U is very large, we get both bands. So we have two orbitals, remember, the black and the red. The red is the wide and the black is the narrow. We get the lower Hubbard band and the upper Hubbard band, and we get an insulator, so no density of state at the Fermi energy. On the opposite case, when U is very low, we have a metallic solution for both bands, the red and the black. This is the lower Hubbard band and the upper Hubbard band. We also see these inner edge features in our results, and we have a finite density of states in both bands, so both are metallic. But we see some structure already within this this gap. If we go to an intermediate value of U, here we have considered a U prime whose difference with U is 0.3. So if U is 3, U prime is 2.7. And in this case, we find an orbital selective mod phase in which the white band is metallic, red, and the black band is insulating, because we have no density of state at the Fermi energy, but we do find some strange feature within the gap and located at the difference U minus U prime, which is 0.3. We have identified these peaks, these in-gap peaks, as produced by holon-doublon quasiparticles of this sort. So here we have the two bands, the wide band at the top, the narrow band at the bottom. And these holon-doublon quasiparticles consist of a hole and a doubly occupied site, which are bound together and are itinerant in the system. So as long as one of the bands is metallic, that will form holes, and that hole will bind to a doubly occupied state in the other band and will produce these densities, these peaks of quasiparticles, peaks at finite energy. The energy is U minus U prime, because if you look at atomic spectra, it costs U minus U prime to go from this, which is the ground state, most relevant state, this 1, to the 0, 2 state. So this was interesting for the half-filled two-band Kanamori-Hubbard model. Now, if you compare to previous results we've seen for the two-band Kanamori-Hubbard, we are able to see structure that hasn't been seen with other methods. So this was interesting. And now, knowing that this structure in the density of states is there, we have also paired with other methods, like, for example, in a collaboration with Kotler and his student in that time, we have always using slave spin mean field decoupling. This structure has also been observed in these systems, like we show here, comparing to our previous results. So here again, you see the half-filled two-band Kanamori. These full lines are the result from the slave spin decoupling. So here, this is the sum of the low energy part. Our data has dots, and the slave spin decoupling has full lines. So we see this very good. There's a very good agreement between both methods. Later on, so this is last year, using numerical organization group as the impurity solver, Kotler and collaborators have also, Weichselbaum, etc. They found that in the three-band Kanamori-Hubbard model with two degenerate orbitals and a different orbital for different values of the crystal field, they're also able to see the structure now with NRG as impurity solver. So here we have the density of states for the degenerate orbital in blue, which is metallic, and in red we have the Mott insulating band. So we are in the situation of an orbital selective Mott case, and here we find some structure in the NRG peaks, but well, they're quite broad. It's difficult to see, but they are here, so they should be at these energies, which are calculated from the atomic limit. And here to the right, we see a much detailed example of structure calculated with the NRG as impurity solver. So this is interesting, knowing that there is structure. Then if we look for it now with other methods, now we are able to find it because we have to refine these other methods. So finally, these are our very recent results. We have uploaded this to the archive yesterday, so they should be there today. And what we studied here is, again, the two-orbital Kanamori-Hubbard model. We can also calculate the three-orbital, and we expect to see this in the three-orbital Kanamori-Hubbard model. So as you see here, we have a lot of structure, and this is where I want to concentrate. So remember now, we're studying the model of the two-orbital Kanamori. So we have a two-orbital system. Now we have the same Hawkins in the two orbitals. We have local U, we have an interband or interorbital coupling U2, which is a U prime, sorry for this mixture, and we also have J. Let's set for the time being J0 now, and let's vary U2, so we would not be in the rotational invariant case, but I mean just to play with parameters. And we find the following. When U prime is equal to 0, we have two separate Hubbard bands, and we're looking now at the doped system. So this is a Fermi energy, or this is a lower Hubbard band. And then here between 3 and 4 omega, we find the upper Hubbard band. This is the Mott gap. What we find here is a very complex structure. Part of it is due to the finite size bath we're using, because we're using the DMRG, but we have only a finite number of bath sites. So this is part of these peaks. Instead of finding a smooth upper Hubbard band, we find finite size peaks, but that can be overseen, and we can just concentrate on the main structure that evolves. What happens if we crank up U prime, which is the interorbital Coulomb interaction? We find that there is a density of states like a band that emerges and comes to lower energies from the upper Hubbard band. And as we crank up U prime even further, this band goes to lower and lower energies until it merges with the low energy structure for this value of U prime, and this value of U prime is U prime equal to U, so it's a rotational invariant case. We have identified this structure that is stripped off the upper Hubbard band as a holon-doublon band. It's represented here by this ket. This ket has the first element will be orbital 1, and the second element is orbital 2. That means that in our effective impurity, we have this state. We have up-down on one orbital, and we have a hole in the other orbital. Or vice versa, we have hole or up down, because I mean this is only a representative. So if you look at the red dots are a response function for creating this excitation here. So as I show you now in a while, we have identified this excitation as mainly formed by these holon-doublon excitations. We can also find other excitation like this in green, which is up means one particle in orbital 1, one particle in orbital 2. It can be up or up down. Here they are not separated because J is 0, and these peaks are related to this excitation here. The arrows are the exact energies obtained from the atomic limit, where the atomic limit is only considering two orbitals and looking at the multiplets from this atomic limit. So we find it interesting. We find very well-defined holon-doublon in-gap states within this the two-orbital Kanamori-Hubbard model when we crank up U prime. So, well, this hasn't been seen with other methods before, and we hope that it can be also found now. We know that there with other methods like NRG or even with exact diagonalization. Now, let's see what happens with J. So we fix the value of U and U prime, and we crank up J. For J equal to 0 is the result we just found. And now when we increase J, we find the splitting, of course, of the levels we have found. This holon-doublon state here in gap, as we crank up J, we can follow the arrows, and it's split into a lower energy peak and a higher energy peak, and this is due to the splitting of the particle of the double particle hopping in the Kanamori-Hubbard Hamiltonian, because we have the holon-doublon, which now hybridizes, and they produce a bonding and anti-bonding state, so the energy separates due to J. And if we look at the green arrows for low energy, we find also a splitting of the of these states here, which are due to the spin flip behavior term in J. So again, I mean, it might be difficult for you at the first sight to distinguish this because we have a lot of finite size structure here. But if one has a trained eye for filtering the finite size structure, one can really see that these states are evolving with J. So finally, we have projected all of these excitations for a particular set of parameters, for example, this set with J equal to 0. And now with different colors, we can see the projection onto different single particle excitation. The black line, again, is a density of states. This is a Fermi energy. We have a metal. We have a dip here, which we don't know if it's due to finite size effects or if it's a real dip. And then, for example, in green, we have the response function of calculating this A major and A minor, which is the response function of creating that excitation. Remember, this band here is a holon-doublon excitation. With this operator X dagger, we create a holon-doublon. That means it's a single particle excitation, so we create a single particle onto a single occupied state while the other orbital is 0. So we are creating a doublon-holon state. We evolve the Green's function, we evolve the state, and then we destroy a full electron. We get the imaginary part of that, and we get a non-diagonal response function. So, I mean, in a different way of saying, each one of these subbands is characterized by a particular excitation. This green one is nearly purely holon-doublon. I'm sorry. The blue one is holon-doublon. I'm sorry, because the upper Hubbard band is way out of this figure. The blue one is holon-doublon. The green one is sigma prime. So when we have single particle, and the red is when we destroyed, we created one particle over on the completely empty state. So well, I mean, this is interesting because we have structure and we have been able to characterize each subband with a particular excitation from the atomic limit. Now before I conclude, I'm coming to an end. I would like to thank my collaborators. So Gaby Kotliar, Marcelo Rosenberg, Masatoshi Imada, Daniel Garcia and Pablo Cornalias in Bariloche, Eduardo Miranda from Brazil, Juriel Núñez Fernandez, who was my PhD student and now is my collaborator, Armando Alicia in Bariloche, also Robin Wetz. Now we are collaborating in more realistic calculations with ab initio. And also I would like to thank my students, Naira Ocara and Hernan Fernandez Garcia, who are working with me now in applying this solver to more complex systems. To conclude, just I would like to stress that unveiling details in the spectral densities of correlated systems helps us to understand the macroscopic mechanisms which lead to their interesting physical properties. This is our aim. To that end, we need sophisticated numerical tools. One of them is the DMFT, the Dynamical Mean Field Theory, which relies heavily on the calculation on complex interacting quantum impurity. I have briefly, and I think incompletely, reviewed the recent proposals for impurity solvers. And we have developed in particular one which is based on the DMRG, which is based on quantum information concepts as impurity solver. This method we developed allowed us to resolve with unprecedented detail the local density of states for a paradigmatic model, which is in this case, a two-band Kanamori Hubbard, but it can be applied to any model. So in the end, well, we hope that all this can contribute to our common goal, which is the understanding of the behavior of nature. And so this, I would like to thank you all for your attention. Thank you very much.
Well, may I ask everybody to unmute yourself so we can give Karen a very nice round of applause. Okay, thank you all. So now the colloquium is open for questions. So the participants on the Zoom meeting can ask the questions by clicking on participants and then using the raise your hand option. And the people at Facebook can ask questions using the chat. So I can, let's see in the list here. So I can see that Marcelo Civelli has a question. Please, Marcelo, can you unmute yourself and make the questions, please?
Yes, hi. This is Marcello Civelli. I'm from University of Paris-Saclay in Paris, the same lab of Marcelo Rosenberg. Thank you for your talk. Hope you hear me well. Do you?
Yes, yes. Hi, Marcello.
Hi. Okay, look, I have a very simple question. I remember that when one solves the simple band-Hubbard model, the Bethe-Lattice limit, with Monte Carlo and some real axis impurity solvers, in the insulating phase, so strong coupling, there are peaks appearing at the band edge in the real axis impurity solvers as compared to the Monte Carlo, for example. Are these peaks, doublon, holon excitations that you have found inside the gap in the two-band Kanamori-Hubbard model? Are the same things or are different kind of excitations? Do you know these?
Yeah, I'm not sure. We are talking about the inner band structure. We see that peak that is right on the inner part of the lower and upper Hubbard band. These are there for the metallic, for the one-band Hubbard model in the metallic solution, and these have been very well studied by Karski, Ras, and other people, and also Weichselbaum von Delft. They have an interesting paper where they, in the metallic solution, they also identify these peaks with holon-doublon excitations in band, holon-doublon excitations, kind of excitations. However, for the insulating states, I don't know. I think one has to really repeat these calculations again, because I don't know how robust they are. I don't know if that structure is...
That's the point. I've seen contrasting results on this point. Some people says that even in the insulator you have peaks appearing at the band edge, and people say no. So, and to me, look, that the point was really real axis solvers had this kind of peaks. So I was wondering if you had the chance.
Yeah, yeah. Yeah, I think this has to be reviewed again because I'm not sure that these features are real in the insulating solution.
Because I think, for example, people like Imada Masatoshi has been discussing this informally as holon-doublon excitations. I never understood very well until I've seen this talk. Thanks a lot.
Yeah, thank you.
All right, bye-bye.
Thank you, Marcello. The next question is from Chimiao C. Chimiao, please.
Hi, Karen.
Hi, Chimiao.
Nice talk. Yeah, so I have a sort of pragmatic methodological question. For NRG, for this kind of impurity-like models, one manages to get some finite temperature, the temperature-dependent information out of the procedure. And I was wondering from DMRG for this impurity or maybe cluster type of models, whether something like that could, in principle, be carried out for the information about the temperature dependence of spectral properties.
Yes, Chimiao, I think this is a very interesting future development you're mentioning because you know that it is possible to include temperature in DMRG. DMRG in general, I say DMRG, but it's also tensor networks or MPS implementation of the DMRG. Including temperature is possible. There have been many different attempts long ago, Mokuri, Caron, also Steve, White, and other people trying to, in different limits, high temperature limit or low temperature limit. So it is possible to include temperature in the DMRG. And as such, it is also possible to include temperature dependence for the DMRG impurity solver. The thing is, it is very computationally very demanding because already for I can see Steve there nodding. Hi, Steve. So if you want to add something, Steve, to this, you're an authority on the DMRG, so welcome. But it is possible, but it is very demanding. Our real access impurity solver is very demanding. It takes a lot of CPU time. That's why we could not go to much larger systems. In addition to the COVID, and we had electrical shortages and all that, but including temperatures. But in principle, it is possible, and I hope someone will do it at some point.
If I may, just to follow up on taking advantage of expertise here, at least from a user perspective. So in NRG, one doesn't really put temperature into the calculation, right? One uses the dependence on the size of the sort of the chain to extract the temperature dependence of certain quantities. I mean, even static quantity would be interesting. And I was just wondering whether there's a computationally manageable way of extracting some information. For instance, for quantum critical properties, one would like to get the temperature dependence of certain static order parameter susceptibility out of the calculation.
Yeah, one could, so there are many different DMRGs. One is the IDMRG, which is not Steve Jobs, it's infinite DMRG. And this is interesting because it's an infinite system, and one evolves the DMRG local or the MPS locally, and it's easier to get temperature dependencies there. So this could also be a possibility, like you're saying. So the answer, Chimiao, to your question is yes, one can include temperature. There are many different ways of dealing with the DMRG or MPS, and even with ancillary states, like Steve has done and other people, that would be interesting to go into. But it's still very.
It might be interesting to follow up on that at this point.
Yeah, it would be interesting. So like Uli Scholbeck and collaborators, what they did with the MPS, by converging on the imaginary axis, the entanglement is much lower. They can do it with very few states. So one could try to do that on the imaginary axis, and again, then do a couple of iterations on the real axis to try to get the solution. But in that case, it's very difficult to get very detailed structure. But with temperature, everything broadens out, and it might be another way of doing it too.
Yeah, thank you.
me also, the next question is from Stevie White. Please, Stevie White.
Hi, Karen. Nice to see you. Nice talk. So my question is, when we do the DMRG dynamics methods, we have two broad classes of methods. One where we solve the Schrodinger equation in time, and the other one we focus on one particular frequency. And can you compare those two methods for use as a impurity solver?
Both are equivalent. Uli Scholberg has also, or the TEBD, they rely on time evolution, like you say. You have also applied, developed very efficient dynamics by evolving in time and then Fourier transforming. So it's completely, of course, valid, and it's an alternative way of calculating dynamics. Now, I cannot compare this as impurity solver, but from our experience on the dynamics of correlated systems, I think the outcome will be, or the comparison will be similar. If you want to go to very low energies, you have to evolve for long times, and etc. I mean, you have this time energy Fourier transformation. But it would be interesting to see the same. I mean, we're doing the DMRG with a correction vector, and we're looking at one energy where our method is highly parallelizable. We can parallelize the program because we do each omega independently, and we send all the omega packet to the cluster. So each omega frequency is run independently, and then we put everything together for the density of states. Now, one can think of how to parallelize the time development. It could also be done, probably. It's still an open question, Steve, but it's completely, I think it should be equivalent. But this correction vector is very useful, and very precise for each omega. Besides, we're also using the Langshaw's solution of the inverting the problem. We do not use the steepest descent. I mean, we have more, other numerical algorithms to invert the Hamiltonian. I still think my impression is that the real omega will be a little bit more efficient than the real time, but who knows?
Okay, thanks. Makes sense.
Any further questions?
I have a question, Pascual.
Go ahead, please.
Okay. Hi, Karen. Thanks for your talk. Very nice. I have, basically two questions. One is methodological. What is the perspective of using DMRG for cluster implementation? In other words, to include more than one impurity in the cluster.
This
okay.
Yeah. This has been done in a way. I mean, we are using, when we use the 2 orbitals or 3 orbitals, this is a cluster because
yes.
it's a single site but it's equivalent. I mean, it's the same.
Sure.
It's the same sort of implementation because our Green's functions are matrices, and now we have a higher dimension in the impurity. So an impurity with 2 orbitals is equivalent to a single orbital Hamiltonian like the Hubbard with 2 sites. Okay. So if you look at Uli Scholberg's results, where he did an impressive implementation of 2 sites with 3 orbitals each. So it's a 3-band Kanamori Hubbard in the 2 sites. So that's a supercluster DMFT. So, well, yes, I mean, you get huge matrices, and if the matrices are diagonal, because you can diagonalize the interaction of the impurity with a band, is easier. But if you have mixed interactions, then you have a completely full and non-diagonal Green's function matrix, and that gets more complicated, and then you have to fit all those parameters to get the effective Hamiltonian for the DMFT equations. So it's a mess. And you have to fit in all that to get the effective Hamiltonian. But in principle, it can be done, but it's very cumbersome.
Okay, thank you. The second question is regarding this holon-doublon excitation, which to my mind, it looks like a sort of a Mott exciton, right? Because it's like a particle hole bound state in a Mott insulator. At least it looks like that to me. Is there any way you can see of experimentally finding a signature for this kind of excitation?
Maybe with optical conductivity, we'll be able to see it, because if you look at optical conductivity, then you have transitions between the different bands, I mean, with the different regions in the density of states, and then I'm sure one can, I mean, my proposal would be with optical conductivity experiments to see if you see a structure in sigma versus omega. It's interesting because really they are, I mean, we saw it for the first time in this, in the two-orbital, in the half-field system where this structure arose, and we saw it. And then when we said, let's see if we dope the system and we create holes, if these holes would be accompanied by these doublons, and we did find them, but they form a band. But the band is purely formed by these things, nearly purely formed. So it's quite interesting to investigate further. I mean, it's completely within this Mott-Hubbard band, and it's not only a fine-tuning of parameters. One can see that it really evolves, and it's got, I mean, it's extracted from the upper Hubbard band, and that makes it interesting. And then it goes down into the low energy, and it merges into the low energy spectrum. And I didn't tell you, I mean, our results on the lock-in of this orbital selective Mott transition, because we find in the case where U is equal to U prime, so this is a highly rotational invariant case, highly symmetric case, where if one band is metallic, even if the other band is very, very narrow, nearly a flat band, the second band remains metallic with a finite density of states on the density and the Fermi energy. And so there is a lock-in of the transition. So there's no orbital selective Mott transition when both U is equal to U prime, when the local is equal to the interbands. And this has been a controversy for a long time between different groups. And we find this lock-in. So what we are seeing is that as long as we have holes in one band, they drag the doublons with them at zero energy when U is equal to U prime. This is a very interesting limit. But the peak we find, the density of states in the narrow band is not a Kondo-like peak, but it's a different kind of a peak. So this is also interesting. The Kondo kind of peak, the singlet for this effective impurity in the metallic is a normal Kondo kind of peak, but the peak on the other band is not, and it has exactly the same weight, but it's a peak that is remnant of the density of states of the mobile holes. I'm a bit sloppy here because I mean it's a whole. I have to show you the figures, but that's interesting.
Okay, thank you.
Any further questions? So I don't see any other questions. So Karen, may I ask you please to stop sharing the screen, please?
Yes. I left it just in case I wanted to show other things.
Okay. So before we finish, so I would like to thank Karen again very much. It was very nice talk and very nice seeing you. So thank you very much for joining us today. And before we finish, I kindly ask all the audience to please start your videos so I can have a print screen of all participants, if that's okay to all of you. So thank you very much for joining us. Stay well, stay healthy. Take care. Nice to see you all.
Thank you.
Thank you so much. Goodbye to everybody. Thanks for coming. Bye.
Bye.
Bye.